Chapter 3 is really just an extension of Chapter 2. We're still working with linear functions, but now we are starting to focus a little bit more on context. So the title of this section is Writing Linear Equations in Slope-Intercept Form. As we know, slope-intercept form is y equals mx plus b, where m represents the slope and b represents the y-intercept. In this context, Sarah starts the month with $15 but spends $2 each day. The amount she has left depends on the number of days that have passed. We want to create a representation of a table, graph, and equation that represents this function based on the context above. So whenever we start talking about a context, we want to identify what do the x values represent. So remember, x are the inputs and the y values are the outputs. So in this case, our x represents the number of days that have passed, or time. And then y represents the amount of money she has left. And those units would be in dollars. So when we think of when x equals 0, that means 0 days, so no amount of time has passed. So we want to look at how much money she started with. So in this case, she started with $15, and that makes our initial value, or y-intercept, 15. From there, we're told that she spends $2 each day. So after one day, that means she would have spent $13 or have $13 left. After 2 days, $11 left. After 3 days, 9, and after 4 days, 7. So our rate of change is $2 per day. Now, if we want to write that as a naked number without units, we would just say 2. From here, if we are going to graph this equation, we can start at our y-intercept and continue down. So at one day, she had $13 left. At 2 days, she had $11 left, and so on. Now, one thing to recognize, if we're looking at this rate of change given the graph, notice to get from one point to the next, it almost looks like I'm going down 2 units and to the right 2 units. But it's important to recognize that our scale of our x-axis is 2 squares for every 1 day. So even though this looks like it's 2 units, you're still only adding 1 day to the previous amount, whereas you're going down by $2. So actually, I need to change this rate of change to -2 since we are decreasing. And that makes our equation y equals -2 times x plus 15. We could also write this in a different order and say y equals 15 minus 2x. And they would both mean the same thing. So to formally define a linear function, all linear functions have a constant rate of change. And in this case, constant just means stays the same. So in the example above, that rate of change was -2 because she was spending $2 each day. That never changed. And this causes the graph of a linear function to form a straight line. So we've talked about this a little bit before, but how can we determine the equation of a linear function, specifically in slope-intercept form? Well, we've said that every line is defined by its slope and its y-intercept. So those are the two things that we most likely need to find. So I'm going to say determine the rate of change or I can use slope. Remember, those mean the same thing. And these three are just different ways of thinking about that. So rate of change is your change in outputs divided by change in inputs. Visually, we can think about the rise over the run from point to point, or we also have a formula looking at the difference in the y values divided by the difference in the x values. The second thing that defines a line is the y-intercept, or we might say the starting point. If it is not given, we can always find what the starting point is based on the rate of change. We'll look more at that in section 3.2. So looking at a few examples, the first one is very straightforward. If our slope is 4, that's our m value. And if our y-intercept is -6, that's our b value. So then the equation is simply y equals 4 times x minus 6. So we're always multiplying our rate of change by the input. From example 2, first, if we want, we can identify that our starting point is at -1. And then to get from point to point, I have a rise of 2 and a run of 3. Right, since I'm going up, that's an increase of 2, and to the right is an increase of 3. So both values are positive, and that makes my equation y equals 2/3 x minus 1. If I'd like, I could also write this as y equals -1 plus 2/3 x, but notice it doesn't change my slope or my y-intercept. Taking a look at example 3, we are given 2 points and asked to find the equation of the line. So we know that these 2 points lie on the line. If you're a visual person like me, you might want to do a quick sketch, and the point -3, 1 would be here, and the point 0, -8 would be down here. So from there, we can recognize that our starting point is at -8, but then we have to calculate the rate of change. So we're going to look back to our difference in our y values divided by the difference in our x values. So sometimes it can be helpful to label those. So in our first ordered pair, we have x1 and y1. And in our second ordered pair, we have x2 and y2. So from here, the difference in my y values would be -8 minus 1. And the difference in my x values would be 0 minus -3. So if you need to use a calculator here, go ahead, but this should simplify to -9 divided by +3. So note this is the same as 0 plus 3. So then my rate of change simplifies to -3, and that's my m value. So I have my slope and my y-intercept, allowing me to write the equation y equals -3x minus 8. Now, the fact that we are given 2 points that lie on the line, and I'm saying this equation represents the line, I can check that I have the correct answer by substituting one of the points into my equation. So if I substitute -3 in for x and then 1 in for y, if it is indeed a solution, the equation should then be true. So I'm going to do that now. And when I simplify, -3 times -3 minus 8 does tell me that 1 equals 1. Therefore, I have the correct equation. So I want you to take a moment to think about how example 3 and example 4 are similar but potentially different. So remember, in example 3, these points are called ordered pairs. So we're given two pairs of inputs and outputs. So in example 4, that's actually the same thing. It's just stated a different way using function notation. As we can recall, this number still represents our input and this number represents our output. So once again, I'm actually given 2 points that fall on the line. So once again, since x is 0, I know that -2 is my y-intercept, and I can use that calculation for the difference between the x and the y values to determine my rate of change. So I'm just going to color code this to show that I'm taking the difference between my y values and then the difference between my two x values. And that equals -1 divided by 4. So that is my value of m. Putting those two things together gives me an equation, y equals -1/4 x minus 2. If I want to write this with a decimal, I can, and say y equals -0.25x minus 2, and it still would represent the exact same line or function. Finishing up with example 5, we have another context. In this scenario, the initial fee to have a website set up using a server is $48. It costs $44 per month to maintain the website. We want to write an equation that gives the total cost of setting up and maintaining a website as a function of the number of months it is maintained. So before we start identifying the rate of change in the starting point, we want to label what our inputs and our outputs represent. So we have total cost and we have number of months. Which do you think is X and which do you think is Y? So if you said the number of months is X and the total cost is Y, then you are correct. Notice the total cost is in units of dollars, and the units really for X is number of months, which represents time. So in this case, our rate of change is $44 per month. So notice that corresponds to the units. Y is dollars and X is months. So change in the Y value compared to the change in the X value. If I want to write this as a naked number, I would just say equals 44. And then my starting point, which is the initial fee, is $48. And notice the units of the starting point are the same units as the y values or the outputs because this is the y-intercept. So then our equation would be y equals 44x plus 48. So to use this equation to give us an actual information, we want to determine the total cost for a website for 6 months. So that means x is equal to 6. So first I'm going to show you what this looks like with just our naked numbers in the equation. And that simplifies to a total of $312. But the units here are important, and it also shows you why the equation is set up the way that it is. So we have $44 per month multiplied by the 6 months that we are maintaining the website plus the initial setup fee of $48. So when simplifying this, notice the months divide out, and all we need to do is take 44 times 6, and we are left with $264 plus the initial 48 to give us a total cost of $312. So that's why we're taking the rate of change and multiplying it by X, and that ends up converting those units to the same units as the output so that I end up with the number of dollars. So at this point, go ahead and pause the video to try the next two questions on your own. Once you've tried them, go ahead and hit play to check your answers. So for A, the equation ends up being y equals negative 2/4 x plus 1. You may have simplified the rate of change, and that would be the same as y equals negative 1/2 x plus 1. For problem B, we calculated the difference between the y values and the difference between the x values to get a rate of change of 11/6, and then we had a y-intercept of 2. So hopefully at this point you've recognized that every linear function is defined by its slope or rate of change and its y-intercept or its starting amount.